Good morning everyone. In vector calculus and complex variable unit 2, today we are going to see integration of vector. In integration theorem there are three types: Green's theorem, Gauss divergence theorem and Stokes theorem. So for our first topic is Green's theorem. Here there is a problem. Verify Green's theorem in the plane for integration C 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the boundary of the region defined by x equal to y square and y equal to x square. Here 2 points are given and also the value of a plane is given. So we take this point as a parabola. So both are parabola. Here see the diagram. So x equal to y square denote the upper parabola and y equal to x square denote the right side parabola. So I am taking those points touching each other as A and B. So first upper parabola denoting x square equal to y and right side parabola y square is equal to x. The center point A 0, 0 and the point which touches both the parabola as B 1, 1. The Green theorem formula is integration C u dx plus v dy is equal to double integral r tau v by tau x minus tau u by tau y dx dy. Here C denoting the curve and r denoting the region. Thus in the solution we can take the given plane as it is and also the given points and write the Green's theorem. First we have to find the right hand side and also the left hand side. Our both the values should be equal. So I am taking first right hand side. So first we have to take the u value in our given statement. So u value is 3x square minus 8y square and the value of v is 4y minus 6xy. When we differentiate u with respect to y, we get minus 16y, and differentiate v with respect to x, we get minus 6y. So I am taking the right hand side formula, that is double integral r tau v by tau x minus tau u by tau y dx dy is equal to double integral r. Substitute tau v by tau x, so the value is minus 6y and the formula minus the value of tau u by tau y value is minus 16y and dx dy. Now solve this. Minus into minus is plus 16y minus 6y, so we get 10y dx dy. Here the inner integral represent the axis x and the outer integral representing y. So when we solve for x, we get the limit inner limit lies between y square to root y, and also we know that the value of y is 0 to 1. Now take the 10 as constant outside, so the remaining is integral 0 to 1. Keep y outside. When we integrate with respect to dx, we get x with the limit y square to root y dy. Substitute upper integral minus lower integral, so we get y into root y minus y square dy. Then multiply this y inside, we get y power 3 by 2 minus y cube into dy. Now we have to solve this integration for y. So we get y power 5 by 2 divided by 5 by 2 minus y power 4 by 4 with the limit 0 to 1. While substituting upper limit, that is 1, we get 2 by 5 minus 1 by 4. Now we have to multiply the denominator, that is 5 into 4 is 20, and cross multiply the numerator with the denominator. 2 4s are 8 minus 1 5s are 5. So we get 8 minus 5 by 20, that is 3 by 20. Cancel out 0 on both the numerator and denominator. We get 3 by 2. Thus we found the value for the right hand side of our Green's theorem formula as 3 by 2. Similarly we have to find the value for left hand side, that is the value of left hand side is 3 by 2. So for that we have to take the value as a to b. In the diagram we see a to b and b to a. For a to b, we have to substitute the integral value as 0 to 1, and for b to a, we have to substitute the limit value as 1 to 0, that is along ab and along BA. So along AB, that is our upper parabola value is y equal to x square. Differentiate with respect to x, we get dy by dx is equal to 2x, that is dy equal to 2x dx. So for the value of y and dy, we have to substitute these values. Okay, so our Left hand side formula of Green's theorem is integral C u dx plus v dy, that is along AB. So substitute the value of our plane inside and substitute for y and dy, that is y square. Y can be written as x square. Here there is y square, so it can be written as x power 4 and 6xy. For the value of y we can substitute x square, and the value of dy we can substitute 2x dx. In the third step we have to multiply this 2x inside the bracket, so we get 8x cube minus 12x power 4 dx. So we get in the first term and the second term both are in dx, so we can take dx as common outside, so write the remaining term in bracket. So it is going along AB, so along AB means we can substitute the limit as 0 to 1. Now integrate this term with respect to x. We get 3x cube by 3. X power 4 can be integrated as x power 5 by 5 and x cube can be integrated as x power 4 by 4. Now we have to substitute the upper limit minus lower limit. So upper limit value is 1. So we get 3 by 3, that is 1 x cube minus 20 by 5, that is 4 x power 5. 8 by 4, that is 2 x power 4, 0 to 1. Upper limit is 1 and the lower limit is 0. So when we substitute upper limit we get 1 minus 4 plus 2, that is 3 minus 4, which is equal to minus 1. Thus I find the value for the axis along AB. Then we have to find the axis along BA. Then we have to add both the things for the left hand side. So for along BA, udx plus v dy. Now substitute the plane equation inside our integral. So for the right hand side parabola, we can take y square is equal to x, differentiate with respect to x, we get 2y dy by dx, which is equal to 1. So dy 2y is equal to dx. Here we can substitute the value of x and dx as y square and 2y dy. So substitute in this. In this term we can take dy as common and write the remaining part in the bracket. Now we have to solve for y. So integration of y power 5 is nothing but y power 6 by 6, y cube is y power 4 by 4, y is y square by 2, again y cube is y power 4 by 4 with the limit 0 1 to 0, because this is going along BA. So BA means we have to substitute the limit as 0 to 1. When we substitute the upper limit we get 0 minus lower limit is 1. So 6 by 6 minus 16 by 4 plus 4 by 2 minus 6 by 4. When we solve this we get the value as 5 by 2. Now we found the two value for the left hand side, that is the value one is minus 1 and another value is plus 5 by 2. When we solve this we get 3 by 2. Already we saw on the right hand side we found the value 3 by 2. Here in the left hand side we found the value as 3 by 2. So both left hand side and right hand side of our equation is equal, hence Green's theorem is verified. This is the first method in integration theorem. Second one is Gauss divergence theorem. Here we can see the formula for Gauss divergence theorem is double integral S f vector n cap ds, which is equal to triple integral v del dot f vector dv. That is, we have to find the value of right hand side and also for the left hand side. Both the side must be equal, then we can prove that the Gauss theorem is verified. First of all, see the problem. Verify the Gauss divergence theorem for f vector is equal to 4xz I vector minus y square j vector plus yz k vector over the cube bounded by, so the lines are given x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, z equal to 1. So for our right hand side formula there is a triple integral, so we can substitute the inner integral as x, then y, outer integral as z. So all the integral value is lies between 0 to 1. So in our question they have given us cube. So here see the diagram. I can take the cube value in x, y, z axis. So the bottom of the cube is denoted as O, A, E, B, and the upper of the cube is denoted as C, D, G, F. Similarly front and back. Similarly one side, another side. So that is the 6 faces of our cube has taken in as surface S1, S2, S3, S4, S5, S6. If I take the front part as S1, that is surface 1. So I can refer it as unit outward normal vector n cap as I vector. So similarly S2, surface 2, that is the back side of the face, that is denoted as minus I vector. So S3 surface is one side, that is J vector, another side is minus J vector. So upper side is K vector and down side is minus K vector. So here we can see the problem, the solution. Now we can take the formula for Gauss divergence theorem. So double integral S F vector dot n cap ds is equal to triple integral V del dot F vector dv. Now we have to substitute for the right hand side. That is, we know the F vector, that is our given vector. Del dot F vector, first substitute for I. So if we solve the I vector for x, we get 4z. Then we have to solve for j, we get 2y. Then we solve for k, we get y. So that is del dot F vector is nothing but 4z minus y. Now we have to substitute this in Gauss divergence theorem. That is triple integral v del dot F vector into dv. That is triple integral 0 to 1. So value of del dot F vector is nothing but 4z minus y. So dv is, there are 3 limits. So we can substitute dx, dy, dz. Now we have to solve this thing with respect to x. So 4z can be written as 4xz minus yx with the limit 0 to 1. Okay, when we substitute the upper integral 1, we get 4z minus y into dy dez. Now we have to solve this integral with respect to y. So we get 4yz minus, so y become y square by 2 with the limit 0 to 1 dez. Now we have to substitute the upper integral minus lower limit integral. We get 4z minus 1 by 2 with respect to z. Next we have to integrate this with respect to z. So we get 4z square by 2 minus z by 2 with the limit 0 to 1. First we have to substitute the upper integral minus lower integral. When we substitute the upper integral, we get 4 minus 2 minus 1 by 2. So the lower integral is 0. So now we have to solve this. 4 by 2 minus 1 by 2, the value is 3 by 2. Thus we found the value for the right hand side. That is, the value of the right hand side formula of Gauss divergence theorem is 3 by 2. Similarly, we have to solve for the left hand side of Gauss divergence theorem. So our left hand side formula is double integral S F vector dot n cap ds. So here they denoted as a cube. So it has 6 surfaces. So for the 6 surfaces we have to solve this. For the surface 1, double integral S1 F vector dot n cap ds, we have to take the face AEGD. So AEGD is nothing but AEGD. So front face of this. Now we have to substitute the value of F vector and the value of n vector. See the above unit outward normal vector, that is n cap. So the value of n cap is I vector dy dz. If we take the x-axis, then we denote this as dy dz. Now we have to solve, multiply both the thing as I vector. So only we get the I vector value 4xz dy dz. Now so for the integral we can take 0 to 1, 0 to 1, because all the 3 vectors are in 0 to 1. Now we have to solve for x. We get x equal to 1 on surface 1. So 4 is a dy dz. Now we have to integrate this with respect to y. We get 4yz with the limit 0 to 1 dz. When we substitute 1 for y, we get 4 is a dz. Now we have to integrate this with respect to z. So z dz will become z square by 2 with the limit 0 to 1. Now we have to substitute the upper limit and lower limit. We get 4 by 2, that is 2. Now we found the value for the front side. Similarly for the back side, we can substitute it as minus I vector for n cap. So take minus 4xez dy dez. We know that the x equal to 0 on surface 2. When we substitute x equal to 0, we get all the integral will become 0. So our surface 2 will become 0. So third surface 3, double integral S3 F vector dot n cap ds is nothing but we can take E, B, F, G, that is one side of the cube. So that is denoted as J vector into dx dz, because this third surface is denoted in y axis. So it can be take as dx dz. Now we have to multiply the j vector. So only we get minus y square dx dz. We know that on surface 3 y is equal to 1. So we get take minus on outside. So double integral 0 to 1 dx dz. Now we have to solve for x. So x with respect to 0 to 1 dz. When we substitute the upper integral, it will be 1. So integration dz become z 0 to 1. So minus is 0 to 1. Upper limit is minus 1. So for the surface 3, we find the value as minus 1. So the fourth surface, opposite of j vector is nothing but minus j vector. Multiply the j vector, we get minus into minus is plus y square dx dz. We know that on surface 4, the value of y is 0. So our surface 4 will become 0. So surface 5. So we can take the top of the cube. We get k vector. So substitute n cap for k vector. So multiply the k vector values, we get yz dx dy. So double integral 0 to 1. We know that z equal to 1 on surface 5. So we get y only, y dx dy. Substitute solve for x, we get x only with respect to 0 to 1. When we substitute the upper value, we get 1. Then integrate y dy, we get y square by 2 with the limit 0 to 1. Upper limit, so we get half. Similarly for the surface 6, we get the bottom of the cube, we get minus k vector. So multiply the k vector, we get minus y z k vector. We know that on the surface 6, the value of z will become 0. So our surface 6 will become 0. Now we have to add all the surfaces, that is s1, s2, s3, s4, s5 and s6 values. So we get the answer as 1 plus 1 by 2 is nothing but 3 by 2. Here we found the value for left hand side of our Gauss divergence theorem formula. We already found the value for right hand side is 3 by 2. Similarly here also we find the value of left hand side as 3 by 2. Thus left hand side is equal to right hand side. Hence Gauss divergence theorem is verified. In the integral theorem, the third method is Stokes theorem. Here we can see the formula for Stokes theorem. Integration C f vector dot dr is equal to double integral s del cross f vector dot n cap ds. So del cross f vector is nothing but curl. Similarly, we can take the right hand side and prove on answer, and left hand side the same answer will come. So both the left hand side and right hand side must be equal. See here in our problem, verify Stokes theorem for a vector field defined by the f vector x square minus y square I vector plus 2xy j vector in the rectangular region in the xy plane bounded by the lines x equal to 0, x equal to a, y equal to 0, y equal to b. First we have to see the diagram for this. So the rectangular area given, so we can take this area as x-axis and y-axis. The x-axis is denoted as y is equal to 0 and y-axis is denoted as x equal to 0. So the opposite of y equal to 0 is nothing but y is equal to b, and also the opposite of x equal to 0 is x equal to a. So we can go with the line as AB, BC, CD and DA. So because there are 4 faces in the rectangular side. So here we can see our question as a solution. Take the f vector axis and also given line, then write our formula for the Stokes theorem, that is integration C f vector dot dr vector is equal to double integral s del cross f vector dot n cap ds. So here we have to we know that dr vector is nothing but dx I vector plus dyj vector plus dz k vector. Now multiply this dr vector with the f vector, we get x square minus y square dx plus 2xy dy. Here dz is rejected because there is no k vector in our given f vector. Now for our right hand side formula, we have to multiply del cross f vector, that is nothing but I vector, j vector, k vector. Our second row is 2 by 2x, 2 by 2y, 2 by 2z, and our third row is f1, f2, f3. So the value of f1 is x square minus y square, value of f2 is 2xy, and there is no f3 value. So now we have to expand this modulus value. We get 4y k vector. Thus we find the value for del cross f vector as 4y k vector. Now we have to take the right hand side of our Stokes theorem formula, that is double integral s del cross f vector dot n cap ds. So for del cross f vector we can substitute 4y k vector, and for n cap we can substitute it as k vector into dx dy. Why we take k vector for n cap is, so there is no I vector and no j vector, so only k vector we can substitute for n cap as k vector. Now we have to multiply this k vector, we get 4y dx dy. Now we have to substitute for the integral, that is the inner integral represent the x-axis and outer integral represent a y-axis, that is the inner integral x denoting the limit as 0 to a, outer integral as y 0 to b. Now solve for dx, we get x with respect to the limit 0 to a, substitute the upper limit, we get a dy. Now we take 4a as constant outside. Now solve for y, that is integration y dy is nothing but y square by 2 with the limit 0 to b, substitute b for y, we get b square. So cancel out 2 and 2 in the numerator denominator, we get 2ab square. Thus we find the right hand side of our Stokes theorem formula as 2ab square. Similarly we have to find the value for left hand side of this Stokes theorem. So left hand side is nothing but integration c f vector dot dr vector. In our question they are asking for rectangular region. So rectangular region has actually 4 sides, that is see the diagram, a to b, bc, cd and da. So we have to solve for these 4 faces. First for the face ab, so ab, see the diagram, for the ab we can take the line y equal to 0, differentiate this y with respect to x, we get dy by dx equal to 0, then solve for dy, we get answer as 0. Now we have to substitute this value of y and dy as 0. Now to take the integral, integration c f vector dot dr vector is nothing but integration b x square dx. So that is the limit is from 0 to a, because this is going along a to b, so 0 to a. When we solve for x square we get x cube by 3 with the limit 0 to a, upper limit if we substitute we get a cube by 3. Thus we find the value along AB. Similarly for we have to find along BC. So BC is nothing but the line denoting x is equal to a, differentiate this x with respect to y, we get dx by dy is equal to 0. Substitute for dx we get 0. Substitute this x value and dx value in our given formula, we get answer as a b square. Similarly for the axis along CD, that is y is equal to b, dy by dx is equal to 0, dy value is 0. Now substitute this y value as b and dy value as 0 in our given equation, we get a b square minus a cube by 3. Now along DA, that is from top to bottom, we get the line x equal to 0, differentiate this with respect to y, we get dx by dy is equal to 0, we get dx is equal to 0. When we substitute this x equal to 0 and dx equal to 0 in our given problem, we get the answer for the surface as 0. Now we have to add all the 4 sides to get the left hand side value. Integration c f vector dot dr vector is nothing but a cube by 3 plus a b square minus a cube by 3 plus a b square. So cancel out plus minus of a cube by 3, we get 2ab square. We already found for right hand side of the Stokes theorem as 2ab square. Here we find the value for left hand side Stokes theorem 2ab square. Thus left hand side and right hand side of our Stokes theorem are equal. Hence Stokes theorem is verified. Thank you all.